Today we want to look at another part of integration, specifically integrating the function one. This is not integration part. This is not integrating part one. This is integrating the function one. Let's be more specific. Integrating the function one. So if we set up the definite integral from a to b of the function 1 dx, the antiderivative is x, we evaluate from a to b, we get b minus a. B minus a is the length of the interval from a to b. B minus a is just the length of the interval. We can see this in a picture. We know it's the area where height is 1 and our length of the interval is from a to b, so just b minus a. In this case, since one of our dimensions is 1, the area that we're getting is just the length. The same thing happens if we integrate a double integral, the function, integrate 1 over a region. So the same thing happens. If we integrate over a region R, the function 1 dA, this will give us the area of region R. This will give us the area of the region R. For the same reason. We take the area and multiply by a constant height of 1, and we're not changing the value, we're just changing the units. So if we just leave 1 with no units, the integral over R of 1 dA will be the area of the region R. So this is a 1 with no units. We should make sure that this works. So if you recall, yesterday, we've been slicing up this box where y goes from 0 to 3 and x goes from 0 to 9. One of the regions that we dealt with was this upper triangle here. I think we had called it R3. The y equals version of this line is y equals 3/9 x. The x version of that line is x equals 3y. And so a double integral over R3 the integral over R3 of f of x, y dA can be written as a couple of double integrals. One of the ones that we did, y went from 0 to 3. While y goes from 0 to 3, we will need x to go from 0 to 3y. So this is the double integral describing this integral of f of x, y over R. Let's actually make this calculation. let's calculate this double integral. Now I realize I haven't told you how to do, what would these be? Like if partial antiderivatives. I haven't told you how to integrate functions of more than one variable. I'm just observing that. I'm not saying that I'm about to tell you how to integrate functions of more than one variable. You're going to take your partial derivative stuff and do that backwards. I guess I just did. There you go. You're welcome. That's the sum total of that. It's just training at this point. So I just said that if we integrate the function 1, if we let f of x, y equal 1 and integrate that, it should give us the area of the region. The reason I'm picking this particular region is because we already know what the area of this region is. It's going to be half of 3 times 9. So 27 over 2, 13 and a half. So we know what the area is supposed to be. And if we don't get that, then there's something wrong. So let's integrate. Let's let f of x, y equal 1. So we'll have the integral from 0 to 3. And then from, 0 to 3y, just the function 1 dx dy. So we have this iterated double integral. So we just do things a piece at a time. I did call it an iterated integral yesterday, so we're just going to do iterated stuff, do it a piece at a time. So first, the first integral is a dx. So the integral of 1 dx is just x evaluated from 0 to 3y. That's just the result of that first, that inside integral, the first integral. We still have to integrate this from 0 to 3 dy. But this is iterated, so we're just going to do things a piece at a time. The integral of x from 0 to 3y is just 3y minus 0. So this will be the integral from 0 to 3 of 3y dy. Like I said, it's going to be easy. So we just integrate 1 dx. That gives us an x. We plug in the endpoints from 0 to 3y. And now we have an integral with just y in it. That's why we can use functions of upcoming variables. So we first integrate with respect to x. Now we integrate with respect to y. The integral of 3y with respect to y is 3/2 y squared. And then this needs to get evaluated from 0 to 3. Plugging in the 3, we get 27 over 2 minus 0, which is exactly what we expected. 27 is the area of the rectangle. Half of that will be the area of the triangle. recall that we had two double integrals. We had two iterated double integrals describing R3. This was the dx dy. There's also the dy dx integral. So the dy dx integral will go from 0 to 9 on x. And then y, for a typical x value, the y starts at the line and goes up to 3. So in R3, describing the dy dx integral, y is going to go from the line 1/3 x up to 3. And we'll integrate the function 1 dy dx. In this case, we're going to integrate in the other direction. We're going to integrate y first and then integrate x. So here, the integral of 1 dy is y. And then we're going to evaluate that from 1/3 x to 3. This then we're still going to have to integrate from 0 to 9 dx. So right now we have y, but we're about to plug in a function of x. That'll give us a function of x. We can integrate with respect to x and run out the variables. So we're going to integrate from 0 to 9 the function 3 minus 1/3 x. The antiderivative of 3 minus 1/3 x dx is going to be 3x minus 1/3 times x squared over 2, so 1/6 x squared. And this needs to get evaluated from 0 to 9. The 3 times 9 is 27. 1/6 of 9 squared is 27 over 2. Still the area of the triangle R3. If we got something different here, one of them is wrong. It could be that both of them are wrong, but if we get different values for our two double integrals, one of them has to be wrong. But that does not preclude that both are wrong. Does that make sense? And definitely don't just average the two numbers and say that's the answer. That answer's got to be somewhere in the middle. What? So unsurprisingly. How's everybody okay? I can't not say it because even though y'all are in top 3, I can't not say it, but the way I got the 1/6 of 9 squared, 9 squared is like 3 to the 4th. So this part here is 3 to the 4th. And then we take a 3 out of the 6th, leave a 2. Take a 3 out of the 3 to the 4th and leave a 3 to the 3rd, which is the 27 over the 2. It's not just because I knew it was going to be 27 over 2. I know some of you are looking at this like, oh yeah, of course, but others of you were grabbing your calculator for that. So just say the obvious thing. Say the obvious thing. That's my new policy. Question? Comment? Snyder Mom? So the point of this exercise was that integrating the function 1 gives you the size of the thing over which you are integrating. So if we go up one higher level and we integrate over a solid dv, like a function of 3 variables, if we integrate the function 1 over a solid dv, that's going to give us the volume of the solid over which we are integrating. I want you to think that the number for the area of this room is equal to the volume of this room if the height is just 1 unit. Those numbers will be the same. Integrating the function 1 gives you the size of the thing over which you are integrating. How's everybody okay? We want to build more double integrals. We just need practice building double integrals. Let's suppose that the region R is the circle x squared plus y squared is equal to 9. Now, before we mention that we're using rectangular coordinates to describe a round thing, which is a very bad idea. We'll see why it's a bad idea momentarily. It actually only becomes a bad idea if I call, don't just set up the integral, actually integrate it. At that point, you're like, oh, then I'm using different coordinates. Because this is round stuff, and these are square coordinates. Those don't fit together. But some of you are like, oh, no way, man. I love trigonometric substitution. So bring it on. At which point I'm like, oh, that's fine. That's okay. So the main thing that we need to understand is that we can't describe this one circle with one function, where y is a function of x or x is a function of y. We need 2. We can say that x is the plus or minus the square root of 9 minus y squared. The plus is the top, or is the right half of the circle. The minus is the left half of the circle. So we can write this. We can solve for x and say x equals plus or minus the square root of 9 minus y squared, where the right half is the plus square root and the left half is the minus square root. We can also solve this for y and get the top and the bottom. and all the symmetry. It makes everything look the same. So there's the top half is the plus square roots, and the bottom half is the minus square root. Let's set up some double integrals for this region. And we can do this in two orders. We can do a dx dy, where our first integral is an x integral, or the other way around. We're setting up a double integral. The protocol is to do the easiest thing first. Always do the easiest thing first. So first, we'll take care of the one that has to be constant. Y goes from -3 to 3. We'll be able to describe the bendy bits with the x. The last integral only gets to use constants, so the last integral is the one that you should write down first. We'll get the bendy part by taking a typical y value and say, what's x between? Here's a typical y value. What's x between? X is between the left half of the circle and the right half of the circle. So x will go from the negative square roots of 9 minus y squared to the positive square roots of 9 minus y squared. There's a dx dy double integral where the region is this circle, x squared plus y squared equals 9. Not the only one that we could have done. We can also set up a double integral the other way, dy dx. Yep, so in a dy dx integral, the x would go from -3 to 3, and the y would go from the bottom half to the top half. So if I pick a typical x value, then we're connecting the bottom half to the top half. So y will go from the bottom half of the circle to the top half of the circle. Two double integrals describing the region, where the region is this circle with the radius 3, center 2, origin. So in these two double integrals, the region is the entire circle. Any questions? Once we get this idea, it's easy to kind of like partition out this circle. So for example, if I just wanted the left semicircle, So I just want this part. What's -3 and what's 0? So there could be some -3 to 0 going on in here, but we can't just say it goes from -3 to 0 because what is it? At this point in your career, using the word it becomes very dangerous. This is especially true for those of you who haven't been through linear algebra yet. In linear algebra, just remove the word it from your vocabulary. Take it right out. It's just going to cause problems.
So for X algebra, was it -3 to 0?
-3 to 0. So the left semicircle with X, we can go from -3 up to 0. And then the Y will remain the same because I want the top and the bottom half. So Y can go from the bottom half of the circle to the top half of the circle. So this is our dy dx integral. We can also build this as a dx dy integral. As a dx dy integral, y goes from -3 to 3. That's the top from the bottom to the top. But x is going left to right. X starts off at the left circle, but stops at 0. So you can still, we're still playing the what's x between and what's y between game. Any questions? Always start by describing the last one, the last integral first. Right now, we're practicing setting up the integrals. Setting up the integral is the point of the problem. That's what we're trying to learn because we spent all the last 2 semesters learning how to evaluate these integrals. Now we're learning how to set the problems up. We set some problems up last semester too. Not we, because y'all weren't in my class for Calc 2. I don't actually know what you did. I'm just guessing. Just playing the percentages. Any questions? How's everybody okay? This is super useful. It's always funny when math teachers are like, oh, this is super useful because they have to point that out because it's not obvious that this is super useful. If you recall, think back to Calc 2. One of the things that you did was you calculate the volume of some solid by slicing a sphere, let's say, into a bunch of circles. And then you're like, oh, dude, we already know the volume of a sphere. And then the first twist was like, okay, what if the radius is 3 and I cut 1 unit off the top? Just slice 1 unit off the top. Where's your volume formula now? And you're like, oh, well, I don't have one. It's like, oh, good thing you have integration. And then to emphasize that point, we're like, oh, what if the density of the sphere varies from top to bottom? The tricky part there was we had to vary the density in the same direction that you were slicing it because you only had one variable to work with. In this picture, I could have a variable density that doesn't change just in one direction. Before, I would have to say the density is I don't know, proportional to the distance from the x-axis. So the density was constant at all these different y values. Well, that's a single integral that we could set up. But with 2 variables in play, I can vary the density all over. I can have different density at each point x, y, as long as I can write some function representing that density. And I would just calculate the mass as the density times the area. And it would just, instead of, then f of x, y would have the area function, 1, and the density function, some function of x and y. But we're not just locked into having the density vary in one direction. We have more freedom in what we can set up when we get to use more variables. On one hand, that makes the setup easier. On the other hand, that makes the setup more difficult because we can consider more things. How's everybody okay? So one of the things that we notice in this particular problem, right now we set up this double integral, and it doesn't seem to be really a problem because we're not actually doing any calculations, right? This whole mismatch between the round thing and the rectangular description isn't a problem because we haven't done any calculations. But if we wanted to say, find the area of this circle, I know we know what the area of the circle is. We want to make sure that our double integral will work. If we wanted to use our double integral to find the area of the circle, we're going to run into a problem. Because if I wanted to calculate the integral from -3 to 3, then the integral from negative square root of 9 minus y squared to positive square root of 9 minus y squared, the function 1 dx dy this is where we're going to run into difficulty because there's a mismatch between the shape of our thing and the coordinates we're using to describe it. Oh, the other thing I want to point out is notice that in this, when I wrote down this double integral, I didn't say y equals and x equals. That is, we get that from the dx dy at the end. The dx here says these are the x's. The dy here says these are y's. So we don't have to write the x equals and the y equals. I write the x equals and y equals because we're new and we're practicing. But later on, you're not going to write that. It's like writing 1x when you first start doing algebra. It's like, well, 5x minus 4x is 1x. And then later on, you're like, all right, now if you want to be cool and fit in, you don't write the 1. You just say x. And then every time we do that, we get mad at Elon Musk. I'm going to call my company X now. I spend all that effort calling it tweeting and just get rid of that. Yeah, dumbass.
Yes,
Because now it's like, oh, and it's just X. It's like, oh, like the website. So we integrate with respect to X, and it's fucking time now. I'm gonna have to start using a different variable. I'm gonna switch to theta or something. We integrate with respect to X, and we just get X. And evaluate from negative square root to positive square root. We still haven't integrated dy. That's where the problem is going to be. We plug in the endpoints and subtract, which means we'll have a square root minus a minus square root, so we'll have 2. And now we get to the thing that we always get to when our rectangular coordinates are describing round things. We would have to do trigonometric substitution. The reason I phrase it like that is because I'm not going to do this trigonometric substitution. But it's at this point, you'd be like, oh, ew. Trig sub. Unless you're like, yay. Trig sub. I don't know how you feel about that. The thing that we want to note, the reason that this is a problem is that we're using very round things, a circle, and describing it with very rectangular coordinates. That's the problem that we're getting to. Using rectangular coordinates to describe round things can lead to some problems. Complications. It's not impossible, it's just less convenient. Question? How's everybody with trig sub? Everybody remember trig sub substitution? Which case of trigonometric substitution is this? What tells us what the case is? The negative sign in front of the y. So what case does that make this? No, there's what are the three trig cases, trig substitution cases? Secant. What else? No, just secant. Secant case. Tangent case. Sine case. Those are the three that we use. The reason that 9 minus y squared is the sine case is that 9 minus y squared is akin to the 1 minus sine squared. 1 minus sine squared becomes cosine squared. That's the point of the trig sub. Takes two terms that are under a radical, usually under a radical, takes two terms and becomes one term. It's trig function Thunderdome. Two terms enter, one term leaves. 9 minus y squared, when we do the substitution, will be 9 minus 9 sine squared, which is just 9 cosine squared. So we get 3 cosine. If it was 9 plus y squared, then we want to use the squared plus squared trig identity, which is 1 plus tangent squared. 1 plus tangent squared is equal to secant squared. 2 terms enter, 1 term leaves. And if it was y squared minus 9, that's when we want to use secant, because it's secant squared minus 1 is tangent squared. That's how you remember what the three cases are. They're tied to those Pythagorean identities. And the Pythagorean identities take two terms and make one term. Then all we have to do is remember how to integrate even powers of cosine and odd powers of secant without tangent. If you do your trig integral, if your theta integral is also a substitution, you messed up. Go back to the original problem and find out the substitution you could have done back then. If you do your trig substitution, you get an even power of cosine or an odd power of secant without tangent. Then you just have to remember how to do those.
They can't help you.
No, trig tables can help you. Integral of secant is natural log of secant plus tangent, right?
Yeah, you-
Am I right or am I lying to you?
I don't.
What do you do for secant cubed? It's not substitution. So what do you do if it's not substitution? I'm starting to see where people fall yay or nay on the trig sub. Maybe you're starting to see where I fall into yay or nay trig sub. It's because I have trig classes. I'm like, oh, dude, this is fucking awesome. Especially when you remember why the cases work the way they do. If you remember the point of doing the exercise, then it helps. And since the integral of secant cubed, you do by parts. The part that you integrate is secant squared. The part you differentiate is. It'll iterate back. So if your professor's a real dick, he gives you like the integral of secant to the fifth. Because you have to do parts and then parts. And it doesn't loop because it's not a polynomial.
And then one of the part, you have to put this place.
Yeah, and then of course you'll drop a constant somewhere. And eventually it drills down, the parts lead to, you have to know the integral of secant is natural log of secant plus tangent. Any questions, comments, snide remarks? That's because trigonometric substitution is our favorite. It's just so weird. So yeah, this is sine case because it's a 1 minus sine squared. All right. So this is our x. This is the thing that we're working on. Multiple integrals. What's x between? What's y between? What we have to do next is describe some round things without using rectangular coordinates. Let's use some round coordinates for describing round things. That would be much healthier for our mental health. That's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.
But, nice guy.